For decades, scientists trusted the cosmic blueprint, the Lambda CDM model, to explain everything, from the mysterious pull of dark matter to the universe's accelerating expansion. Then the James Webb Space Telescope shattered that certainty. In a moment that left Nobel laureates stunned, Webb glimpsed galaxies that are too massive, too old, and too organized to fit our standard story. Galaxies that shouldn't even exist, just a few 100 million years after the Big Bang. Nobel winners are now sounding the alarm. It's another universe. If even the architects of modern cosmology are questioning reality, what else is lurking beyond what we thought was possible? The answer may change our understanding of existence itself. The Lambda CDM model has been the backbone of modern cosmology for decades. It's a recipe with just 6 ingredients, yet it explains nearly everything we see in the universe. At its core, about 5% of the universe is ordinary matter, the atoms that make up stars, planets, and people. But that's only a sliver. Nearly 27% is dark matter, an invisible glue that binds galaxies together, holding them in shapes that would otherwise fly apart. The rest, an astonishing 68%, is dark energy, a mysterious force stretching the universe faster and faster, like an endless cosmic rubber band. This model doesn't just describe what's out there, it predicts how the cosmos should behave. Gravity, powered mostly by dark matter, pulls matter into vast webs and filaments, forming galaxies and clusters. Meanwhile, dark energy pushes space itself to expand, accelerating the separation between galaxies as time rolls on. These two forces, one pulling, one pushing, have shaped everything from the smooth glow of the cosmic microwave background to the intricate patterns of galaxy clusters seen today. Lambda CDM also lays out a timeline. After the Big Bang, the universe cooled and expanded, letting the first atoms form. Gravity got to work, sculpting tiny ripples in the early plasma into clumps of matter. Over billions of years, these grew into galaxies, stars, and planets. The model predicts when the first stars should flicker on, how quickly galaxies should build up, and even how heavy elements like carbon and oxygen spread through space. But there's a catch. Dark matter and dark energy are invisible, detected only by their effects. We can't see or touch them directly. The model's power comes from how well it matches what telescopes observe. The way galaxies rotate, the patterns in the cosmic microwave background, the distribution of galaxy clusters, and the speed at which the universe expands. For years, every new observation, no matter how distant or faint, seemed to fit this cosmic blueprint. The numbers lined up, from the faintest afterglow of the Big Bang to the swirling arms of spiral galaxies. Lambda CDM became the standard by which all new discoveries were measured, a cosmic compass for astronomers charting the unknown. But when a model is this successful, even the smallest cracks matter. The Lambda CDM framework sets strict boundaries on how quickly galaxies can form, how massive they can get, and how early complex structures should appear. Any object found outside those lines isn't just a curiosity, it's a challenge to the very rules that have guided cosmology for a generation. That's why when new data begins to strain these boundaries, scientists pay close attention. The stakes aren't just about one galaxy or one observation, they're about the foundation of our understanding of the universe itself. James Webb was never just another space telescope. From the moment its gold-plated mirrors began to unfold, astronomers saw it as a kind of time machine, one that could capture the faintest glimmers from the universe's earliest days. The mission was clear. Show us what happened less than 400 million years after the Big Bang, when the first stars and galaxies were supposed to flicker into view. That's a cosmic blink after time zero, and well before the galaxies we see with Hubble. The design was ambitious. Webb's primary mirror stretches 6.5 meters across, about the size of a tennis court, giving it more than 6 times the light-gathering power of Hubble. Those 18 hexagonal segments, coated in a whisper-thin layer of gold, are tuned for infrared light. That's the key, because as the universe expands, the oldest light stretches out, shifting from visible to infrared. Webb's detectors are built to catch those ancient photons, the ones Hubble can't see. But building a telescope this sensitive comes with its own set of challenges. Webb needed to stay cold, really cold, to avoid swamping its own detectors with heat. That's why it sits at the second Lagrange point, or L2, nearly 1.5 million kilometers from Earth. Out there, shielded by a 5-layer sun shield, it chills to just 50 Kelvin, allowing it to pick up the faintest whispers from the dawn of time. The plan was to push the timeline of galaxy formation as far back as possible. Webb's first light goal was simple: confirm the predictions of the Lambda CDM model by spotting the universe's earliest galaxies, measuring their ages, masses, and chemical makeup. Scientists expected to see small, dim galaxies gradually building up over hundreds of millions of years, matching the slow, methodical growth outlined by decades of simulations. Confidence was sky high. Every detail, from the segmented mirror to the mid-infrared camera, was engineered to answer one big question: did the universe really unfold the way our models say it did? Webb was supposed to be the ultimate fact-checker, a tool that could either confirm our place in the cosmic timeline, or just maybe, reveal a few surprises waiting in the shadows. Jade's GS-Z14-0 appeared in Webb's data as a blip so bright it forced astronomers to triple-check their calculations. This galaxy isn't just a record setter for distance, it's a heavyweight for its age. At a redshift of 14.32, its light began the journey to us when the universe was just 290 million years old. That's less than 2% of cosmic history, yet this single galaxy holds a stellar mass of about 320 million suns. For context, that's 100 times more massive than what anyone expected to find at this epoch. The star formation rate, around 22 solar masses per year, averaged over the last 10 million years. For a galaxy this young, that's like flooring the accelerator from a dead stop. But the real shock comes from what's in its atmosphere. Webb's NIR spec instrument picked up clear signs of oxygen and nitrogen, heavy elements that aren't forged in the Big Bang. These atoms require at least one full generation of massive stars to live, die, and explode, scattering their guts into the galaxy's gas clouds. Yet here they are, less than 300 million years after time zero. The oxygen abundance, measured via ALMA's detection of the O388 micron line, clocks in at 6 to 14% of the sun's value. That's not pristine cosmic gas. That's a system already enriched by stellar alchemy. John Mather, the Nobel laureate who helped design Webb, didn't hide his disbelief. They're not quite like what we thought they were, he admitted. They're surprisingly big, bright, powerful, and numerous compared with what we expected. Coming from the man who measured the Big Bang's afterglow, that's a seismic statement, the term making the rounds in the control room, universe breakers. These galaxies aren't just outliers, they're objects that, on paper, shouldn't exist. Jade's GS-Z14-1, the faintest confirmed galaxy at this distance, adds more fuel. It packs about 40 million solar masses into a region smaller than 50 parsecs. So dense and compact, it's unresolved in 16 NIRCam bands. Its star formation rate, about 2 solar masses per year, means it could double in size in just a few cosmic blinks. Yet even here, the signs of chemical maturity are unmistakable. Population synthesis models suggest metallicities of 3 to 8% solar, with the caveat that dust and gas conditions in these early systems are still a guessing game. Here's where the numbers get slippery. The stellar masses and star formation rates depend on assumptions about how stars form, how much dust is hiding the light, and what kind of stars dominated the early universe. If the initial mass function was top-heavy, favoring giant stars, then the true mass could be lower. But even after accounting for every modeling uncertainty, the masses remain stubbornly high. Some teams have tried to explain the brightness by invoking gravitational lensing, but the best lensing models for Jade's GS-Z14 and 0 suggest only a modest magnification, around 1.17. That's not enough to erase the anomaly. The result? A galaxy that, by every standard lambda CDM simulation, should be vanishingly rare, if it should exist at all. Simulations using standard cold, dark matter, and ordinary star formation physics can produce a handful of such objects, but not in the numbers Webb is now finding. And the chemical fingerprints, oxygen and nitrogen, not just hydrogen and helium, mean these galaxies have already cycled through at least one round of star birth and death, compressing what should be hundreds of millions of years of evolution into a cosmic sprint. The staff at Webb's Mission Center, seasoned by decades of data from Hubble and Spitzer, found themselves staring at spectra that simply didn't add up. The phrase "another universe" started as a half-joke. Now, with each new detection, it sounds less like hyperbole. The cosmic dawn, once thought to be a slow, methodical process, is looking more like a fireworks finale. Brighter, faster, and more chemically complex than anyone dared predict. Adam Rees has spent years measuring the universe's expansion, chasing down every possible source of error. Now, with the James Webb Space Telescope in orbit, his team finally had the tool to settle a cosmic dispute that's been simmering for a decade. The problem? 2 ways to measure the Hubble constant, the universe's expansion rate, kept giving answers that simply didn't match. Local measurements, using Cepheid variable stars and Type 1a supernovae, pointed to a speed of about 73 kilometers per second per megaparsec. But when cosmologists looked to the early universe, reading the subtle ripples in the cosmic microwave background, the number came out lower, closer to 67. The gap wasn't shrinking, it was growing. The hope was that Webb's sharper vision could cut through the haze. Its infrared eyes could pick out Cepheid stars in distant galaxies, even in crowded, dusty regions where Hubble struggled. That's where the SH0ES project came in. Rees and his collaborators set out to cross-check every rung of the cosmic distance ladder, using Webb to revisit the same galaxies Hubble had already measured. If the tension came from hidden errors, blended stars, miscalibrated brightness, or dust clouds, Webb would catch it. The results were unambiguous. Webb's images resolved individual Cepheids with a clarity that left little room for doubt. In all, over 1,000 Cepheids across 8 supernova host galaxies, and the anchor galaxy NGC 4258 were measured. The distances matched Hubble's results to within 0.01 magnitudes, less than a 1% difference. Stellar crowding, once a prime suspect, was ruled out at more than 8 sigma confidence. That's not just a statistical fluke, that's a cosmic lock. The numbers didn't budge. Webb's recalibration pinned the local expansion rate at 73.4 kilometers per second per megaparsec, with an uncertainty of just 2.1. Compare that to the 67.4 measured from the Planck satellite's readout of the early universe, and the gap stands at more than 5 sigma, well past the threshold physicists use to declare a discovery. The odds of this being a random error? Less than 1 in a million. Other distance indicators, like the tip of the red giant branch in the J region asymptotic giant branch stars, were also measured with Webb. They too landed in the same ballpark, 72.2 and 72.1 kilometers per second per megaparsec, respectively. No matter the method, the story stayed the same. Local measurements and early universe predictions simply don't line up. For Rees and his team, the message was clear. The crisis wasn't a mirage. With measurement errors ruled out, something deeper must be at play. Either the physics of the early universe isn't as simple as the textbooks say, or there's a new ingredient hiding in the cosmic recipe. The need for an overarching explanation has never been more urgent. The Hubble tension isn't going away. It's staring everyone in the face, more sharply defined than ever. Roger Penrose doesn't just ask what happened at the beginning, he asks if there even was a beginning. In 2020, the Nobel Committee recognized his work on black holes, but for decades, Penrose has been quietly building a different kind of cosmic blueprint. His idea? The universe is not a one-off explosion, but an endless series of cycles, what he calls eons. Each eon is a universe, stretching from its own Big Bang all the way to a cold, empty future. And when all the matter is gone, when even black holes have evaporated, what's left is pure energy, massless and smooth. At that point, Penrose argues, the geometry of space can be mathematically transformed, conformally, so that the infinite future of one eon matches up with the birth of the next. There's no hard wall, no singularity, just a handoff, aeon to aeon, forever. Penrose's framework, called conformal cyclic cosmology, hinges on this idea of a massless future. Over unimaginable stretches of time, every particle with mass must decay or lose its heft. All that remains are photons, neutrinos, and gravitational waves, particles that don't care about the scale of the universe. In this massless state, the universe forgets how big it is. According to Penrose, that mathematical trick makes it possible to stitch the end of one universe to the beginning of the next, like cosmic origami folding back on itself. The geometry at play here isn't just a mathematical curiosity. Penrose's conformal mapping means that the far future of one eon becomes indistinguishable from the hot, dense conditions of a new Big Bang. There's no need for a singular starting point. Instead, the universe is reborn again and again, each time carrying faint imprints, subtle clues, from the eon before. It's a vision that trades a single creation event for an infinite cosmic relay, with each universe passing the baton to the next. This cyclical cosmos isn't just philosophy. Penrose has proposed that if this model is right, we might detect fingerprints from previous eons in the cosmic microwave background, subtle patterns, maybe even leftover energy from ancient black holes. The math is dense, but the core idea is simple. The universe is timeless, its story endlessly repeating, with each cycle leaving a whisper in the next. Roger Penrose spent years hunting for clues that might outlast a single universe. His theory, conformal cyclic cosmology, predicts that the universe doesn't just begin and end, it cycles, leaving faint fingerprints from one cosmic era to the next. The best place to look for these fingerprints? The afterglow of the Big Bang, the cosmic microwave background, or CMB. It's a map of the oldest light in the universe, stretched across the sky like a faded photograph. But Penrose noticed something odd in that ancient glow. Nearly perfect circles, each about 8 times the diameter of the full moon, scattered in places that shouldn't have any special meaning. These circles, he called them Hawking points, show up as subtle hotspots, as if something energetic happened at those locations before our universe began. What could leave such a mark? According to Penrose, the final moments of black holes from a previous universe, evaporating in a last burst of Hawking radiation, might do the trick. If his model is right, these Hawking points are the echoes of cosmic events from an eon before ours. Teams pored over Planck and WMAP satellite data, finding hints of these circles, but the evidence sparked fierce debate. Some analyses claimed 99.98% confidence. Others, using stricter statistics, dropped that to 87%. The circles remain controversial, but the idea they represent a bridge between cosmic cycles is hard to ignore. Now here's where things get wild. The James Webb Space Telescope is uncovering galaxies that seem too mature, too massive, and too chemically evolved for their age, just a few 100 million years after the Big Bang. Some physicists wonder if these galaxies are relics, not just of our universe's early days, but of a previous cycle. Could the same cosmic hand that drew Hawking points in the CMB have seeded these impossible galaxies? The connection is tantalizing but unproven. Webb's findings and Penrose's circles both hint at a universe with a longer memory than anyone expected. Yet the story is far from settled. Are these hot spots in ancient galaxies whispers from an earlier cosmos, or just statistical ghosts and cosmic overachievers? For now, the evidence sits on a knife's edge, inviting more questions than answers. The next chapter in cosmic exploration is already being written. The Nancy Grace Roman Space Telescope, set to launch later this decade, is designed to scan the sky with a field of view 100 times wider than Hubble's. Roman will map millions of galaxies, building a massive census of cosmic structure and dark energy's fingerprints. Meanwhile, the European Space Agency's Euclid mission is underway, tracing the distribution of dark matter across time using gravitational lensing. And on the ground, the extremely large telescope in Chile is preparing to resolve individual stars in distant galaxies, pushing the limits of what we can analyze from Earth. Looking even further ahead, the LISA mission aims to detect gravitational waves from merging black holes in the early universe, offering a new way to probe cosmic history. Each project brings sharper tools and broader surveys, promising to test the wildest predictions sparked by Webb's discoveries. For scientists, the roadmap is clear: more data, deeper questions, and the chance to catch the universe breaking its own rules yet again. If galaxies are popping up where they shouldn't, what does that say about the universe you live in? Maybe the rules of cosmic evolution aren't as ironclad as we thought. Or maybe there's something stranger going on, something hiding in the background of every deep field Webb captures. Could these ancient, massive galaxies be the universe's way of hinting at a deeper order, or a crack in the story we've been telling ourselves since the Big Bang? If the cosmos can surprise Nobel laureates, what other secrets could be waiting in the dark? And if our best models can be outsmarted by the faintest smudge of light, what does that mean for the next question you ask or the next answer you trust? The universe is talking. Are we ready to listen? In 2023, the James Webb Space Telescope revealed galaxies like Jade's GS Z14-0 existing less than 300 million years after the Big Bang, with masses scientists did not expect so soon. These findings, confirmed by Nobel laureates such as John Mather and Adam Rees, challenge the lambda CDM model that has guided cosmology for decades. The persistent Hubble tension, where Webb and Hubble measurements of the universe's expansion rate differ by more than 5 sigma, remains unresolved despite rigorous cross-checks. Sir Roger Penrose's conformal cyclic cosmology, recognized by the 2020 Nobel Prize in Physics, offers one possible framework, but no consensus exists. Documents, peer-reviewed studies, and JWST data all agree our map of the cosmos is incomplete. With the Roman telescope and ELT set to launch in the coming years, the scientific community faces its greatest puzzle in a century. What lies beyond our current models remains unknown, but the evidence is clear. The universe is stranger than we imagined.